Hello, physics. I hope you're all doing great and had a great Easter break and are ready to get going on the things that we need to get going on. I know that I had said that we are going to be working on the Rube Goldberg machine project. I'll do an introduction to that on Wednesday, but I need to do a couple things. It does combine aspects of Chapter 10 and Chapter 11. If you want to get a little bit of a preview on it, you can click on the grade link assignment that says Rube Goldberg machine, and it will end up counting in several categories, so you'll be able to kind of look at that. But I'll be getting more information out to you on Wednesday regarding that. So for right now, we need to get going on this whole idea of the work-energy theorem. And then tomorrow we'll talk about some different types of energies, and those will be the things that you end up putting into the machine. So first off, we have our old friend delta back. Delta K, change in kinetic energy equals the amount of work that was done. And this works great as long as you're thinking about just the thing that's moving isolated from all of the other things and friction and all that. So we use this as a starting point. Work-energy theorem means that it's been proved to be true that when you have a change in kinetic energy, that is the amount of work that was done. So K2 minus K1, just like usually when you have a delta, it's the later one minus the earlier one. And that's going to equal the work. Okay, work-energy theorem. What we can do with a little bit of algebra is add K1 to both sides. So what that really is telling us is that the amount of kinetic energy that you have later equals the amount of kinetic energy that you have earlier plus the work that you put into it. Think back to our example when we were talking about changes in momentum, that if you had somebody who was there was a soccer ball and it was going, and then somebody came up running in the same direction and gave it a kick and gave it an impulse, they would be able to propel that ball so that it's going to gain some kinetic energy, but that really is the amount of work that was done on the ball that's being added in. Energy and work have the same unit, joules, because they are so closely related with this whole idea of a change in kinetic energy is brought about by some work that's done on the system. So sometimes it helps to see it as a bar graph. From what I've found, if it helps you, great, and you can draw them. But the part A always says to draw the, on these problems is going to tell you to draw the bar graphs. You can draw them if you want to, but the important part is for you to be able to get the problems correct. So this is what this would look like. You could have your starting kinetic energy and you add some work. And if this was a perfectly drawn graph, it would be this amount of kinetic energy plus this amount of joules of work would be the new kinetic energy, which would be more up above. Or if you had a certain amount of kinetic energy and you had negative work, so yes, there can be negative work, like if that kick was in the opposite direction, you're putting in some negative work on it, or you're pumping the brakes or something like that, then you've got the kinetic energy is reduced, so it becomes less. So you have various different things that can happen during these, and we will get into them more as we progress. But today we're just going to do one example problem, and then your main task is going to be to work on practice problems 1 through 4 that you probably will be able to finish them during the class period time if you're diligent. I want you to do your best to be keeping up on things, because your main focus during the next couple weeks is going to be on that Rube Goldberg project, but we need to make sure that you're also learning the material for Chapter 11. So take the time that I give you to actually work on the correct things. So let's take a look at an example. You have a car, 875 kilograms, and it's speeding up from 22 to 44 meters per second. So we need to calculate its initial and final energies. It says energies, but we're going to say specifically kinetic energies because we know that there's some energy stored up in the gasoline in the car and various other things. But just in the simplest, we're going to look at the kinetic energy and how much work was done in order to change that velocity. Okay, so the first kinetic energy is, if you remember the formula for that from other chapters, is 1/2 mv squared. And if you don't remember that from other chapters, please write it down. Kinetic energy is 1/2 mv squared. Does involve mass, does involve velocity, just like our momentum does, except this one uses the velocity twice. It's much more, the speed is much more of a factor in the kinetic energy than it is in the momentum. So 1/2, 875 is the mass of the car. Then the velocity, it's the K1's the beginning velocity. So whatever it is, make sure when you do these problems that you are unraveling what the beginning part and the end part is. So for example, if you had a car that started from rest, that would be a beginning type of a thing. But if you had a car that was moving and then stopped, that would be an ending type of a number. For right now, we have two. We have a beginning and we have an ending. So our starting initial 122. And so that gives us 211,750 joules. And for those that like to calculate it out, which you should, just to make sure that you're using your calculator correctly, just make sure that you pause it here and there so that you can check your answer after you've done the calculation instead of phasing out. So K2, 1/2 mv squared, 1/2 mass, velocity squared, 44. Here's our 44 comes in. And just doing the calculation, you end up with 847,000 joules. It's saying how much work was done, but remember our work-energy theorem tells us that the work done equals the change in kinetic energy. In other words, the kinetic energy after minus the kinetic energy before. So 847,000 joules minus 211,750 joules. And just by doing that math, you get the appropriate number of joules, and that is also equal to the amount of work that was done. Once again, work and energy are both measured in joules. Now, keeping that in mind, notice in this I have kilograms for car. Okay, kilograms is the SI mass unit that needs to go into these type of calculations. Meters per second is also the unit that needs to be used. So you have to evaluate before you start going, making sure that your units match up with what the SI units are, so that you have it in meters per second and not miles per hour and not kilometers per hour. So we need to go back over the conversion just a little bit before you get going on your questions 1 through 4 on the practice problems. In this particular chapter, you have practice problems and you have a study guide. I have not yet released the study guide because I want you focusing on the practice problems for right now. Meters per second into kilometers per hour. Don't forget, you're going to try to cancel out the meters. You're trying to cancel out the seconds. So we have to remember that there are 3,000. This part will cancel out and turn it into meters per hour, but we then need to cancel out the meters and turn it into kilometers. And there are 1,000 meters in 1 kilometer. So the meters cancel out. Remember, these are nothing more than just some fancy ones. Multiply 45 times 3,600 divided by 1,000. Or short answer is multiply 45 times 3.6 and you get 162 kilometers per hour. Now this is useful maybe at the end of the problem after you have found how fast something is going by leaving variables in and solving equations. But Don't forget that if your beginning information starts in kilometers per hour, you can't use it. You have to change it into meters per second before you can use it. So just in the way of review, the process going backwards, 3,600 seconds in 1 hour so that we can cancel out the hours and get seconds. 1,000 meters in 1 kilometer. Notice they're just upside down, and how you tell, remember, is you're trying to find out what's going to cancel out. So in this case, you're taking 35 divided by 3.6, and we get 9.72 meters per second. Remember, whenever you're doing a problem like this, you've got to have these units in meters per second or it doesn't work as far as that goes. So if you have kilometers per hour first, change it. So there's some good thinking questions in practice problems 1 through 4. Right now, you're done with the lesson for today. Yes, I know there's more slides, but I want them for tomorrow because I want you to do these practice problems 1 through 4 right now, giving you plenty of time. Please do them. And you're not turning them in today. You're going to wait and turn it in as one assignment at the appropriate time. But what you're doing in class today is working on this. And when you fill out the video evaluation form, it will ask you how far you got. So if you say you didn't do any of them, that's a problem because you should be able to spend a lot of time. This is just a short video. All right? Okay, good. And I'm looking forward to seeing what you come up with Rube Goldberg once we get that all going too. And so have a really good day, and I'll see you when I get to see you.